Hi, this video covers the last section in the course, exponential and logarithmic equations. So those are equations. Exponential and logarithmic equations. So we're going to see different types of equations and strategies to solve them. So the first one is the one-to-one property. It's solving exponential equations using the one-to-one property. The one-to-one property of logarithms. Okay, an exponential function is a one-to-one function. If it is a one-to-one function, it has an inverse. The inverse is called a logarithm with base a. So if the logarithm is the inverse of the exponential and the exponential is one-to-one, the logarithm is also one-to-one. So the one-to-one property says that if x is positive, x is positive, y is positive, a is positive, and not equal to 1, then the logarithm with base a of x equal to the logarithm with base a of y is equivalent to x equals y. So let's start with the first example. We are going to solve. We are going to solve the exponential equation 5 to the x equals 14. Okay, so the problem is this exponent that, well, this variable that is an exponent. The properties of logarithms allows us to bring down that exponent as a coefficient. Well, I shouldn't say a coefficient, but that allows us to bring down that exponent. And we can do that by taking either natural logarithm or the common logarithm on both sides. And I'm choosing natural logarithm or common logarithm because those are the ones that I know how to evaluate. So that's natural logarithm of 5x by the one-to-one property. Natural logarithm of 5 to the x equals the natural logarithm of 14. And the properties of logarithms allow me to bring down that x. Natural logarithm of 5 is a constant. So x is the natural logarithm of 14 over the natural logarithm of 5. So that's approximately, let's evaluate. This is natural logarithm of 14 over natural logarithm of 5. This is approximately 1.6340. Or 1.640. So that is the solution set. On my MATLAB, you will be asked to approximate the solution. So the solution set is going to be the set with that number. Okay, second example. We're going to solve another exponential equation that we cannot solve by using the definition of a logarithm. Like if I had something like in the last problem. If I had something like 5 to the x equals 25 or 125, that would have been easier because we can use the one-to-one property and 5 cubed is 125. But that wasn't the case. Okay, So next example. We are going to solve an exponential equation with exponentials on both sides, but the exponentials have different bases. Okay, the exponentials have different bases, so I cannot use the one-to-one property or any of the techniques we used before. Instead, we can take the natural logarithm on both sides, using the fact that a natural logarithm is a one-to-one. The natural logarithm is a one-to-one function. So natural logarithm of 4 to the 2x plus 3 equals the natural logarithm of 0.6 to the x plus 4. So bring down the exponents. And then we're going to distribute a natural logarithm of 4 and natural logarithm of 4.6 or of 0.6 are constants. So we can distribute. And at the end, that's a linear equation that we are going to solve for x. Okay, so this is a linear equation at the end. Okay, so we can solve this by, we can solve this for x by writing the terms with x on one side and the constants on the other side. Okay, so let's write x natural logarithm of 0.6 on the other side. And the 3 natural logarithm of 4, we're going to bring it to the other side with opposite sign. Okay, common factor is going to be x, so we can factor out x. So that is equal to 4 natural logarithm of 0.6 minus 3 times natural logarithm of 4. And finally, solving for x, that is going to be 4 natural logarithm of 0.6 minus 3 natural logarithm of 4 divided by 2 times natural logarithm of 4 minus the natural logarithm of 0.6. Now that's the answer. That's the exact answer. We are going to round this answer to 3 decimal places, so let's find out. Now we can use grouping symbols. This is 4 times natural logarithm of 6 minus 3 times natural logarithm of 4. So that's 3 times natural logarithm of 4 divided by 2 times natural logarithm of 4 minus natural logarithm of 0.6. Okay, and that's approximately okay, making sure I got this. Oh, okay, I see what the, well, yeah, I made a mistake. That should have been 0.6. So let's try again. Yeah, I made a mistake. So that's 4 times. Yeah, I missed a decimal point. And I need a grouping symbol, so let's try again. So that's 4 times, and then 0.6. Not 0.6, that's yeah, 0.6 natural logarithm, and then minus 4 times, yeah, that 3 times 3 divided by 2 times natural logarithm of 4 minus natural logarithm of 0.6. Okay, so let's try one more time. And that's the correct answer. That's approximately negative 1.889. And that is the solution set. The solution set is that. Writing this down. Okay, there it is. So the solution set is approximately negative 1.899. 8889. Okay, whenever we have exponential equations with base e, we can use the definition or we can use the properties of exponentials. So these are the next examples. Are solving exponential equations with base e. Okay, so we're going to solve the following. We're going to start by solving e raised to the x squared equals 150. Yeah, in the previous two examples, I could have used the common logarithm. If I have e to the x squared equal to 150, I can use the definition of the logarithm, or I can write this equation in logarithmic form. So the equation in logarithmic form is going to be x squared equal to the natural logarithm of 150. Or I can take natural logarithm of e to the x squared, but the inverse with the inverse property, that will become x squared. And x is going to be plus minus the square root of the natural logarithm of 150. This is approximately plus minus, and that's the square root of the natural logarithm of 150. So that's about plus minus to 2.238. And that is the solution set. Okay, the solution set is negative 2.238, comma, positive 2.238. And next problem, we are going to solve e to the 3x plus 2 times e to the opposite of 5x equal to 4e squared. Okay, with the properties of exponentials, with the properties of exponents, we can write everything with the same base. So that's the same exponent. And e to the 3x plus 2 minus 5x is equal to 4 times e squared. What do we have? We can combine the 3x and the minus 5x. So e to the 2 minus 2x is equal to 4 e squared. Okay, so we're going to use the property that we used initially. We're going to use this backwards. This is e squared times e raised to the opposite of 2x. And the e squares cancel out. Okay, so far we have that e raised to the opposite of 2x is equal to 4. And using the definition of the natural logarithm, the opposite of 2x is the natural logarithm of 4. Or x is negative 1/2 times the natural logarithm of 4. Okay, so let's evaluate that. I mean, I could simplify that logarithm, but that's enough to simplify the answer. So that's going to be negative 1/2 that's negative 1/2, times natural logarithm of 4. That's approximately negative 0.693. Okay, and that is the solution set. The solution set of that equation is that. So that's the problem that we just did. Okay, we can also solve exponential equations in quadratic form, like we did in chapter 1, that we had equations that look like quadratic equations. So with the exponentials, we can do that. We can solve an exponential equation in quadratic form. Okay, so that's the next example. We are going to solve e to the 2x minus 5e to the x plus 4 equals 0. And we're going to give exact values for x. Okay, so e to the 2x is the same as properties of exponents, e to the x squared minus 5e to the x plus 4. So that can be solved like a quadratic equation. We can let u be e to the x. And that will become u squared minus 5u plus 4 equals 0. This is u minus 1 times u minus 4. So we know how this goes. Either u is equal to 1 or u is equal to 4, but u is e to the x. Okay. So far, this is what we have so far. And by the definition of the natural logarithm, x is the natural logarithm of 1, but the natural logarithm of 1 is 0, or x is the natural logarithm of 4. So if we keep the solutions in logarithm, if we give the exact values, the solution set is going to be 0, comma, natural logarithm of 4. We usually check the solutions, but just a mental check will show you that this is indeed a solution. If we check 0, we have e to the 0. Well, e to the 0 is 1. So 1 minus 5 plus 4 is 0. And natural logarithm of 4. So that's going to be 16 minus 20 plus 4. 16 minus 20 plus 4 is also 0. So just doing a very quick mental check. So far we have solved exponential equations. And the next equations are going to be logarithmic equations. Now with that, we have a restriction that the number inside the logarithm must be positive. So we need to check. Let's start by solving. Uh, 5 plus 2 natural logarithm of x equal 4. So we're going to give exact values. So first we're going to isolate the logarithm on one side. And 2 natural logarithm of x equals 4 minus 5, subtract 5 from both sides. That's -1. And the natural logarithm of x is -1/2. So x is e to the -1/2. We're just going to keep it like that. Or 1 over e to the 1/2, or 1 over the square root of e. So that's it. So that is the solution set. The solution set. And yeah, we can check it quick. I mean, it won't take too long to check that. If we do a mental check, the natural logarithm of e to the -1/2 is going to be -1/2. So 5 and 2 times -1/2 is going to be -1. So 5 minus 1 is going to be indeed equal to 4. And that is the solution set. The solution set is 1 over the square root of e. And b, so the logarithmic equation, logarithm with base 3 of x squared plus 17, of x cubed plus 17 equal to 4. So for that one, all we do is use the definition of the logarithm, or write the logarithmic equation in exponential form. So logarithm with base 3 of x cubed plus 17 is equivalent to 3 raised to the 4th power equal to x cubed plus 17. Now 3 to the 4th power is 3 multiplied 4 times, and that's going to be 81. Subtract 81 from both sides, and x cubed is 64. So x is going to be 4. And again, a quick check. 4 cubed is 81. Sorry, 4 cubed is 64. 64 plus 17 is 81. And the logarithm with base 3 of 81 is going to be indeed 4. So that is the solution set. The solution set is 4. Okay, so we need to remember to check. So far I have been checking mentally. Now we need to check in the next 2 examples. We actually need to check. I mean, we need to write down the check to because it's not going to be that evident. Okay, so we're going to be checking for extraneous solutions. Let's solve. Natural logarithm of x plus 3 minus the natural logarithm of x minus 1 equal to the natural logarithm of x. Okay. If we have a difference of logarithms, we can combine it as the logarithm of a quotient. So that's natural logarithm of x plus 3 over x minus 1. That's going to be the left-hand side. Equal to natural logarithm of x. And the one-to-one property says that x plus 3 over x minus 1 is equal to x. Okay, so we have a rational equation. We can multiply the x minus 1 on the other side. So x plus 3 is equal to x squared minus x. And that quadratic equation, the resulting quadratic equation, let's write it in standard form. Subtracting x from both sides, we have x squared. Subtract x from both sides, we had minus 2x. And then minus 3 is equal to 0. So that equation, we can solve it by factoring. This factors as x minus 3 and x plus 1. We have two possible solutions, negative 1 and 3. But we're not done yet. We still need to check them. So let's check. Let's check the solution x equals negative 1. So know that that's the equation we began with. And we know that the natural logarithm of a negative number is undefined. So this is not a solution. Because the natural logarithm of negative 1 minus 1 and the natural logarithm of negative 1, if we try to plug them into the original equation, these two are undefined. And finally, let's check 3. Yeah, I shouldn't write x equals 2. So that one is going to be okay. That one is going to be a solution because we have the natural logarithm of 3 plus 3 minus the natural logarithm of 3 minus 1 equal to the natural logarithm of 3. Properties of exponents. This is the natural logarithm of 6 minus the natural logarithm of 1. Let's see what's going on. Okay, that was, yeah, sorry, that was minus 1. Yeah, this was minus 1. So the minus the natural logarithm of 2 is natural logarithm of 3. And a quick check will verify that this is indeed a solution. This is also the same as the natural logarithm of 6 over 2 equals to the natural logarithm of 3. So that one is correct. And the solution set of that equation is 3. So let's look back again. I started with a logarithmic equation. That equation, by using the properties of logarithms, became a quadratic equation. The quadratic equation had two solutions, but only one of those solutions was a solution of the logarithmic equation. And this is in the book. So I'm copying the next problem. number 64. Number 64 on page 469. Okay, we're going to solve that equation. So solve the logarithmic equation and check for the solutions. Okay, properties of logarithms, we can combine the natural logarithm of 3 minus x times 5 minus x. Equal to the natural logarithm of 5 minus 6x, or 50 minus 6x. Okay, so 3 minus x times 5 minus x. And I can remove the logarithm because by the one-to-one property, this is going to be 15 minus, that's going to be minus 8x plus x squared equals 50 minus 6x. So I did two things at once. I removed the logarithms and I foiled the expression inside the logarithm. So let's write this quadratic equation in standard form. That's going to be x squared and then minus 5x plus 6x. That's still minus. And 15 minus 15 minus 50. Okay, we can solve this equation by factoring. That's x minus 7 and x plus 5. The possible solutions are 7 and 5, or negative 5. Okay, so let's check. Let's check negative 5. We have natural logarithm of 3 minus negative 5, that's plus 5. Plus natural logarithm of 5 plus 5. Equal to the natural logarithm of 50 minus 6 times 5. So that's natural logarithm of 8 plus natural logarithm of 10 equal to natural logarithm of 6 times 5. So that actually becomes plus, or times negative 5. Minus 6 times negative 5. So 6 times negative 5, the opposite of that is 30. That's going to be natural logarithm of 80. And properties of logarithms, this is natural logarithm of 8 times 10 equals natural logarithm of 80. So that's correct. So that one is a solution. And we're finally going to check 7. We got natural logarithm of 3 minus 7, and I think that's it. So this is not a solution. Not a solution because natural logarithm of 3 minus 7, natural logarithm of 5 minus 7, and 6 times 7, well, because these two are undefined. The other one is going to be fine. But yeah, we have two undefined expressions. So the solution set is negative 5. So sometimes only one is a solution and sometimes both are solutions. And that is the solution set is negative 5. Or there might be cases when there is no solution. So I was looking for one of those, I couldn't find it. Okay, and okay, so I'm doing one more. I'm doing number 54. One example in which both our solutions. Okay, so that one, we have a single logarithm, so we can just go ahead and rewrite in exponential form. So 4 cubed is 64. And then 3x plus 8 times x minus 6 is going to be 3x squared. And then 6 times negative 6, so that's minus 18 plus 8, so that's going to be minus 10x minus 48 equal to 64. So subtract 54 from both sides, and 3x squared minus 10x minus 112 is equal to 0. We can factor the trinomial on the left side as 3x plus 14 and x minus 8. So 3x equals negative 14, or x equals 8, or x equals negative 14 over 3. Okay, so these are the possible solutions. And we need to check. So I'm going to start by checking the more difficult one. So this is what? This is logarithm with base 4 of 3 times negative 14 times 3 plus 8. So that's 1. Times negative 14 over 3 minus 6. Equals 3. Okay, 3 times negative 14 over 3 is going to be negative 14. So this is negative 14 plus 8 times negative 14 over 3 minus 6. Okay, so I'm just going to go ahead and do this fraction mentally. So negative 14 and 3 times 6 is 18, so that's negative 32 over 3 equals 3. Negative 14 plus 8 is negative 6. So all this becomes negative 6. This is logarithm with base 4 of. And then negative 6 over 3, this is negative 2. And negative 2 times negative 32 is going to be positive 64. Logarithm with base 4 of 64 is going to be indeed 3. And 8, well, I'm just going to skip the check. I did a harder one, but I'm skipping the check. So you can verify. Yeah. 8 is also a solution. And the solution set is negative 14 over 3, comma 8. So I'm going to finish the section, and this is the last video in the course, with applications of exponential and logarithmic equations. The first one is example 10 on page 467. The strength of a habit is a function of the number of times the habit is repeated. If n is the number of repetitions and h is the strength of the habit, then according to a psychologist, they are related by this function with the natural exponential function. So solve this equation for k. Okay, solve for k. So h is 100 times 1 minus e raised to the opposite of k times n. Okay, so let's distribute the 1,000. If we want to solve for k, we need to isolate the term with k. So we're going to interchange these two values. And 1,000 e raised to the opposite of kn is equal to 1,000 minus h. Divide by 1,000. And dividing by 1,000 and e. Okay, so this is what I'm going to do. Divide by 1,000. So e raised to the opposite of kn is equal to 1 minus h over 1,000. Rewrite, now that I have the exponential by itself, I can rewrite in logarithmic form. The opposite of kn is the natural logarithm of 1 minus h over 1,000. Nk is the opposite of 1 over n times the natural logarithm of 1 minus h over 1,000. Okay, so that's the expression in simplest form. I mean, I could use the properties of logarithms, like bringing the 1 over n as an exponent and converting it to the nth root, but that's not going to make things simpler. So we can just keep it like that. And the last one, to finish the course, that's the last word problem. It's on page 471, number 109. The percent of women in the US civilian form can be modeled fairly well by that function below. That function with exponential with base e, where x represents the number of years since 1950. What percent to the nearest whole number of US women were in the civilian labor force in 2014? And in what year were 55% of US women in the civilian labor force? Okay, so x represents the number of years since 1950. And 2014 minus 1950 is equal to 64. So we're going to plug in 64. We're evaluating f at 64. That is 67.21 over 1 plus 1.081 e raised to negative 64 over 24.71. So what I'm going to do is just evaluate this in a calculator. This is 67.21 over 1 plus 1.081. Remember to use grouping symbols for the denominator, times e raised to. So more grouping symbols, negative 64 over 24.71. So let's close parentheses. So that's approximately 62%. So this approximately 62. Or about 62%. And B, in what year were 55% of US women in the civilian labor force? So we're going to make the right-hand side of the function equal to 65. We need to solve the right-hand side is so was that yeah, so that's an X. So that's 67.21 over 1 plus 1.081 e to the opposite of X over 24.71 equal to 55. Solve this for X. Okay, so let's solve this equation. We can start by bringing the denominator to the other side. Okay, then distribute the 55. When we solve this exponential equation, we are going to isolate X on one side. So 55 times 1.081 is 59.455. Okay, next step, subtract 55 from both sides, and 12.21 is equal to 59.455, 455. E to the X over 24.71. Okay, so we're almost there. What I'm going to do next, I'm going to divide the 12.21. I'm going to divide the right-hand side by 12.21. And this exponential with negative sign, I'm going to pass it to the left-hand side with positive sign. Okay, so finally we have isolated the exponential. We have isolated the exponential with base c. Rewrite this equation in logarithmic form, and X over 24.71 is equal to the natural logarithm of 59.455. And X is 24.71 times the natural logarithm of 59.455 over 12.21. Okay, so let's evaluate that expression. This is 24.71 times 59.455. I should use grouping symbol. Yeah, I had to use group. Yeah, I didn't use a grouping symbol. Well, this is what I'm going to do. First, I'm going to calculate the logarithm. Let's first calculate the natural logarithm, and then multiply that by 24.71. 4.71. Okay, so we're going to compute the natural logarithm of that and then multiply by 24.71. And that is 39.11 approximately. Or about 39, approximately 39. Where X represented the years after 1950. So 1950 plus 39 is 1989. So that's the final answer. In 1989, 55% of women were in the civilian labor force. That was 55%. Okay, so this is it. Thank you for listening.